Wheatstone Bridge. This Wheatstone Bridge, it is an arrangement of four resistances which is used to determine one of the unknown resistance. So this Wheatstone Bridge, it consists of four resistances, that is P, Q, R and S. And all these resistances, they are arranged, right, to form a quadrilateral ABCD. So as you can see in this figure, this ABCD, it is a quadrilateral. Okay, now out of these four resistances, three resistances are known. Q and S are unknown fixed resistances. Even this capital R here also, it is known, but it is a variable fixed resistance, which means its value can be adjusted so that, right, we shall see that later, right, it can be adjusted so that the galvanometer, right, gives zero deflection. So to get a zero deflection in the galvanometer, we have to adjust the resistance capital R. Okay, all right. Now, the second part of this is the principle of the Wheatstone Bridge. This Wheatstone Bridge, right, it is based on the principle that when the bridge is balanced, then what happened? The product of the resistances in the opposite arm, that is P into S equal Q into R. P into S is equals to Q into R. Further, we call this Wheatstone Bridge because the point B and point D here, it is bridged with a galvanometer. So this galvanometer, it is actually like a bridge that joins the 2 point B and D. So therefore we call a Wheatstone Bridge. Now, looking at the figure, we see that this point A and point C, they are connected to a cell of EMF E. Now this cell E, it is sending a current I to the Wheatstone Bridge. This current I, right, it goes like this and it reaches at point A. So at point A, this current I will be divided into two parts. Let's say I1 is going along AB, that means through the resistance P, and I2 is going along AD, which means through the resistance R. And looking at this figure, this I1 here, it has to travel to a point B. And at point B, what happened? This current I1 now, it will be divided again into two parts. One is along the galvanometer, the other is along the resistance Q. So out of this I1, let's say the current IG here, it is flowing through the galvanometer. So please note down here that this galvanometer it has a resistance capital G. So if Ig is going through the galvanometer, then the remaining current that is going through the capital Q, right, through the resistance Q, it will be I1 minus Ig. Okay. Also, we have seen here that these two current I2 and Ig, they are meeting at a point. But the current which is leaving this point, it should be the sum of the current, right, that is entering the point. That is I2 plus Ig will be going through the resistance capital S. This is according to Kirchhoffs current law. Okay. Now, suppose I have a key, let's say here. This is a key K1 and I have a key, let's say this is a key K2. Now, if you switch on the key K1 and K2 at the same time, then what happened? The current will be flowing through the circuit in this way. It will be divided along its different parts, and some current Ig will be flowing through the galvanometer. Now, In order to obtain this balance condition, which is, the product of the opposite, the product of the resistances in the opposite arms are equal. So in order to get this condition, what happens is we have to adjust this resistance capital R till the galvanometer give zero deflection. So when the galvanometer gives zero deflection, it means that there is no current flowing through this arm BD, right? That means, in other words, I can say the potential at a point B is equals to the potential at a point D. So when the potential at 2 points are same, then there will be no flow of charge or no flow of current. Okay, so here we shall see about this condition, which is the balance conditions of a Wheatstone bridge. So this condition is known as a balance condition. So now we shall see how do we obtain this condition. Okay, so for that we will apply Kirchhoffs voltage law in two loops. One is A, B, D, A. So in this closed loop A, B, D, A, what are the products of current and resistances in the different branches of the loop? So first, AB. Along AB, the product of current and resistances will be positive. I hope, right, this is clear because I have explained this in the previous video also, that when you are crossing the resistance along the same directions of current, then this product is positive. Similarly, along BD, it will be plus Ig capital G, which is the resistance of the galvanometer. And along DA, it will be minus I2 times capital R. This is your equation. Okay. So these are actually the products of current and potential and current and resistances in the different branches. Now the product of all these resistances and current in different branches, it should be equals to the summations of EMF. But looking at this closed loop, A, B, D, A, do you see any EMF? No. So therefore, the algebraic sums of EMF in this case will be 0. So we name this as your equation 1. Similarly, now we will consider the second loop, that is B, C, D, B. So for the loop B, C, D, B, applying Kirchhoffs voltage law, you will find out the product of resistance and current across this arm BC. It will be I1 minus Ig times capital Q. This is positive because we are traveling across the resistance, right, in the same directions as of current. And then along CD, it is minus because current is going up but we are going down. So the product of current, which is I2 plus Ig times the resistance, will be negative here. And along DB, similarly along DB, the product of current and the resistances will be negative. So everything now will be equals to 0 because again in this closed loop we don't have any such EMF. So therefore the right hand side is 0. Okay. Now, under the balance condition, what happened? Under balance condition, the galvanometer, as I told you, it gives 0 deflection, which means Ig is equals to 0. So when Ig is equals to 0, so equation 1 and equation 2 becomes, now your equation 1 becomes I1P. This is 0, so this term will disappear and you'll have equals I2R, because if you take this to the right, it becomes positive. And equation 2 becomes I1, this is 0, so you'll have only I1Q. I think I made a mistake, this is I2 plus Ig, right? Okay. So even this also will become 0, so you'll have only minus I2S, and this is 0 because Ig is 0 on the balance condition. So keep taking this minus I2S to the right, you'll get I2S like this. Now this is your equation 3. and this is your equation number 4. So if you divide equation 3 divided by equation 4, you will get I1P upon I1Q in the left hand side, and the right hand side you will get I2R upon I2S. Now this I1 cancel, I2 cancel, so you'll get P into S is equals to Q into R. So this is what? This is the balance conditions of the Wheatstone bridge. So please remember, when the bridge is balanced, then PS, the product of resistance in the opposite arm is right. They are equal because QR also is the product of resistance in the opposite arms. Okay. Now from this equation, let me name this as equation 5. From this equation 5, which one is your unknown resistance? Your unknown resistance, it is P. So therefore, if you find out P from here, you'll get QR upon S. Okay. So from this equation, let me name this as equation 6. So from equation 6, right, this unknown resistance, which is to be determined by this bridge, it can be obtained by using this equation, because Q, R and S, they are all known resistances. So therefore this unknown resistance P can be obtained easily using this equation number 6. So this is all about Wheatstone bridge. I hope this video is clear to you.